Welcome. This tutorial is a continuation of my previous video on simple linear regression. In that video, I used data collected from 10 students recording the number of hours studied as x, the independent variable, and grade on exam as y, the dependent variable. We plotted the data points on a scatter diagram and found a positive linear relationship appears to exist. We can see this graphically. As x increases, y also increases, which indicates a positive slope. In the previous video, we calculated the least squares line, also known as the line of regression. Y hat is equal to 55.048 plus 4.74 times x. The slope was calculated using this formula, and we got 4.74 for the slope. Remember, x is the number of hours studied, y is grade on exam. The slope tells us the increase in y for every 1 unit increase in x. So for this example, a slope of 4.74 indicates that for every 1 hour of study, a student's grade should increase by 4.74 points. Next, we calculated the y-intercept b naught using this formula. We got 55.048. Remember, the y-intercept is the value of y when x is 0. That means for this example, when x, the number of hours studied, is 0, grade on exam is predicted to be 55.048. We also calculated the coefficient of determination, r squared, which is SSR divided by SST. Again, if you are unfamiliar with these terms, please review my previous introductory video on simple linear regression. The link for it appears in the description box for this video. Here are the numbers we calculated for the sums of squares. We did this by hand for demonstration purposes, but we will also do this using Excel in this video, which is of course much quicker and much more accurate. Using our hand calculations, we got 0.9505 for r squared. R squared can take on any value between 0 and 1. It tells us the proportion or percentage of variation in y that is explained by x. In this example, r squared is 0.9505. That means that 95.05% of the variation in y grades is explained by x, number of hours studied. Next, we calculated r, the correlation coefficient. This is simply the sine of the slope and then the square root of r squared. We have an r value of positive 0.9749 for this example. R can take on any value from -1 to +1. A -1 would indicate perfect negative correlation, +1 would indicate perfect positive correlation, and of course, if r is 0, that would indicate 0 correlation or no relationship between x and y. For this example, we have an r value of positive 0.9749. This would indicate a very strong positive linear relationship between x and y, since plus or positive 0.9749 is very close to +1 and very far away from 0. And finally, we ended the previous video with a hypothesis test for the slope. We wanted to test to see if the slope was equal to 0 or not. If we rejected the null hypothesis, which we did, then we would show support for the alternative hypothesis that the slope is not equal to 0, indicating that there is a relationship between x and y. We know the sample slope b1 is 4.74 for this example. What we are testing here is whether there is evidence from the sample data to show that the true population slope, beta1, is not equal to 0. Our test statistic, remember we always calculate a test statistic from the sample data to test our hypotheses. Our test statistic is b1 over sb1. By hand, this took a bit of calculating. First, we needed to calculate sb1. But to get SB1, we first needed to calculate S, the standard error, to put into the numerator for SB1. S is the square root of SSE divided by n minus 2. We had already calculated SSE, the sum of the squares for the error, as 79.1215. Since n minus 2 is 10 minus 2 or 8, then the square root of 79.1215 divided by 8 and minus 2 is S, 3.1449. So now that we have S, we can put that 3.1449 into the numerator for SB1, and we get 0.3825 for SB1. Again, you can review all of these step by step in my first video on simple linear regression. The link for that video is in the description box. Now we are ready to put SB1 into the test statistic. So we have B1 over SB1, 4.74 divided by 0.3825, and we get a test statistic of 12.3921. Now that we conducted an hypothesis test on the slope, we can continue here with a confidence interval estimate on that slope. Here you have the formula for a confidence interval on beta 1, the true slope. The sample slope, B1, is 4.74 for this problem. What we want to do is take that sample slope and add and subtract a margin of error so that we have an interval for the true population slope. The formula is B1, the sample slope, plus and minus T of alpha divided in half times SB1. We already calculated SB1 and we got 0.3825. So we have most of what we need from our previous calculations. 4.74 is the sample slope, plus and minus T of alpha divided in half times SB1, 0.3825. We are, however, missing our T value. For a 99% confidence interval, what would alpha be? Well, alpha is 1 minus our level of confidence, so then alpha would be 0.01. Remember, we're constructing a confidence interval here, and with an interval, you always have some values above in the upper tail and some values below in the lower tail. So with confidence intervals, you always split alpha in half. Alpha divided in half here is 0.005. We are using a t-table, so we need degrees of freedom. Degrees of freedom for simple regression is n minus 2, which is 8 for our example, since we have 10 observations. Now let's take a look at our t-value in the t-table under 8 degrees of freedom and alpha divided in half of 0.005, and we get a t-value of 3.355. So now we can take that t-value from the table, 3.355, and put it into the formula for the confidence interval. So we get 4.74 plus and minus 3.355 times SB1, which was 0.3825. That gives us an interval of 4.74 plus and minus the margin of error of 1.2833. So we get a lower interval value of 3.4567 and an upper value of 6.1233. This is a 99% confidence interval on the slope. That means we are 99% confident that the true population slope, beta 1, is contained within this interval. We only know the number 4.74 from the sample of 10 students, but the population slope, beta 1, is not necessarily exactly 4.74. It could be a little more or it could be a little less. By adding and subtracting a margin of error around the sample statistic, we are creating an interval within which we can be 99% confident that the true population parameter exists. Now let's conduct a hypothesis test on the correlation coefficient. Remember, R is the correlation coefficient for the sample. We have a sample of 10 student grades, and we calculated R from that sample of 10 observations. But if we are to have data from the entire population of students, then the correlation coefficient would be denoted by the Greek letter rho, R-H-O. Rho looks like a P, but think of it as an R with a missing leg. Rho is the symbol that we use when we are talking about the population parameter for the correlation coefficient. So we are interested in testing whether or not rho, the population correlation coefficient, is equal to 0 or not. R for this example is positive 0.9749. We know that R can take on values from -1 to +1, and that 0 means no correlation. Our sample correlation coefficient R seems to indicate a strong positive correlation, but this is from a sample of 10 student grades. Is this enough evidence for us to reject the null hypothesis and find support for the alternative hypothesis that rho is not equal to 0? That would indicate a strong relationship or association between X and Y, number of hours studied, and grade on exam. The test statistic we use is a t-test with R in the numerator and the square root of 1 minus R squared divided by n minus 2 in the denominator. In the previous video tutorial, we conducted an hypothesis test on beta 1, the slope, to see if it was equal to 0 or not. Here we're conducting a hypothesis test on rho to see if it is equal to 0 or not. These two tests are really one and the same. We will find the same result. In fact, when we do the calculations here for the test statistic, it will produce the same test statistic, the same result. So let's go ahead and calculate the test statistic. R is a positive 0.9749. So filling in the formula, we get 0.9749 divided by the square root of 1 minus 0.9505 divided by 10 minus 2. R squared is the coefficient of determination. We had previously calculated R squared to be 0.9505. And we get 12.3937. We get a number that is very close to the test statistic that we calculated for the slope beta 1. The number should be exactly the same. The only reason it is different here is because I'm using a handheld calculator, and therefore there are some negligible rounding errors. Not to worry, Excel will give you an exact number. The rounding errors here will not affect our conclusion. Back to what we were doing, our hypothesis test for rho, the correlation coefficient. Our test statistic is 12.3937. So does it fall in the rejection region or the non-rejection region? We had previously looked up a critical value for alpha of 0.01, alpha divided in half 0.005 with 8 degrees of freedom. And remember, we just looked it up. It was 3.355. So 3.355, our critical value, splits our rejection and non-rejection regions. And now we can see that 12.3937, the test statistic, falls clearly in the upper tail rejection region. Our statistical conclusion is then, reject the null hypothesis. There is evidence that rho is not equal to 0 and that a significant correlation exists between grades and number of hours studied. We can also use the p-value approach to come to the same conclusion. For the p-value approach, we use the test statistic, 12.3937, and degrees of freedom 8, and using the t-table under 8 degrees of freedom for the test statistic, we find that it would be off the chart, somewhere here. This would give us a value for alpha that is off the chart, but we can extrapolate and conclude that the value would be close to 0, certainly less than 0.0005. Let's use 0.0005 as the number, even though we know the value would be much less than that. Since this is a two-tailed test, we need to double the value that we looked up. 0.0005 times 2 is 0.001. As before, the rejection rule is reject the null if the p-value is less than or equal to alpha. If we use alpha 0.01, then our p-value 0.001 is less than our alpha value of 0.01. So we reject the null hypothesis. This is the same conclusion as the critical value approach. There is evidence that rho is not equal to 0 and that a significant correlation exists between grade and number of hours studied. One more topic for this tutorial, and then we will look at the Excel output for this set of data. Remember, we calculated y hat, the predicted value of y for a given x value, using the line of regression shown here. We used an x value of 3 to predict y. If a student said that the number of hours they studied was 3, then what would y hat be? Y hat is the predicted grade for that individual response. Plugging x3 into the model, we get y hat is equal to 69.268. So if an individual student value for x is 3 hours studied, then their predicted grade on the exam would be y hat 69.268. But remember, y hat is a point estimate. Suppose we want a more realistic estimate. We would take y hat plus and minus a margin of error. A confidence interval estimate would be a more realistic way of expressing the individual student's response. The formula for calculating the confidence interval for an individual response y for a given x is shown here. Y hat plus and minus t of alpha divided in half times s times the square root of 1 plus h sub I. We already have y hat, that is 69.268. We already looked up the t-value for 99% confidence interval when we calculated the confidence interval for the slope, so let's use that again, 3.355. Also, the standard error, 3.1449, was previously calculated. So all we need to find is h sub I. Here is the formula for h sub I. Let's have a closer look at it. The first part, 1 over n, is easy. N is 10 for our example, so this is simply 1 over 10. Next, we have the numerator for the second part of the formula, x sub I minus x bar squared. That is different than the denominator, which has a summation sign. So the numerator part is for just one x sub I, in this case x sub I equal 3. However, the denominator is the sum of all of the x sub i's, all 10 of them, subtracted from x bar, squared, and then added up. If you look back to the previous video, you will see we already calculated this when we were calculating the slope. So the denominator will be the sum of the squared deviations of each x sub I from the mean, or 67.6. The numerator is the squared difference of just one x sub I, the one we are interested in, x equal 3, and we subtract that from the mean, which was 4.8. Again, look back in your notes from the first video. Now we can calculate h sub I, and we get 1 over 10 plus 3 minus 4.8 squared divided by 67.6, and that is 0.1479. Now let's go back to the original formula for calculating a confidence interval for y hat. We have y hat for x equal 3, and for a 99% confidence interval, alpha is 0.01, alpha divided in half is 0.005. With 8 degrees of freedom, we looked that up and we got a t-value of 3.355. H sub I we just calculated as 0.1479, and S we had previously determined to be 3.1449. So now we need to plug in everything into the formula. Y hat plus and minus 3.355, that's our t-value, times 3.1449, that is S, times 1.0714. 1.0714 is not h, it is the square root of 1 plus h sub I. And that gives us 69.268 plus and minus 11.3044. Let me go back for a second here. This 1.0714, again, is for that entire piece that is circled in red, the square root of 1 plus h sub I. H sub I is 0.1417. So 1 plus that, and then take the square root of that, and you will get 1.0714. When you multiply all three terms out, you get 11.3044. So 11.3044 is the margin of error. And then we get an interval for an individual response of y when x is equal to 3 of between 57.9636 and 80.5724. So we are able to say with 99% confidence that if an individual student studies for 3 hours, so x is equal to 3, then his predicted grade will be, y hat, will be between 57.9636 and 80.5724, which is a more realistic way of predicting a student's grade than to say they'll just get a 69.268. Now let's see how we can get Excel to do most of these computations for us. Here is a worksheet with my 10 data values. First, click on the Data tab and then choose Data Analysis. Sometimes data analysis is not on your Excel ribbon because it hasn't been added in yet. By default, it is not added in. In order to add it in, you have to go to the File menu, click Options, then click on Add-ins, and at the bottom where it says Manage Excel Add-ins, click Go, choose Analysis Toolpack, and click OK. And then the Data Analysis option should appear. Once this is done and you have data analysis in your ribbon, then choose the regression option in the dialog box and click OK. A new dialog box comes up asking for the range of y values and x values. Enter the range for the grades for the y range and hours studied for the x range. Check the labels box if you have labels in your first row as we do, and then check confidence level if you want the output to have a confidence interval. The default is 95% confidence interval. You can see I changed that to 99% for our example. This is the resulting output. The regression equation for our example is y hat is equal to 55.0355 plus 4.742604x. You can see these numbers are slightly different than what we calculated by hand. We get this y hat line from the Excel output very easily. 55.0355 is the y-intercept, b0, and it is given to us here under the column labeled coefficient and the row labeled intercept. The value in the equation of 4.742604 is the slope, b1, and we can find that number under the row for the independent variable x. It says there hours studied, and it is right there where the green arrow is pointing. We can also find r squared here. It actually says r squared. Remember, r squared was 0.950537. The formula for r squared is SSR over SST. So r squared is 0.950537. SS refers to the sum of the squared values, and we can find all of our sums of squares under this column that is labeled SS. SSR is in the row for regression. SST is in the row for total. So we get SSR over SST, r squared, 0.9505. So 95.05% of the variation in grades is explained by hours studied. Remember, r squared is the variation in y that is explained by x. Another number we can get from the Excel printout is S. S is a number we use quite a bit in our various calculations. S is the standard error, and we find it right here, 3.144863. So to review, B0, the y-intercept, is here, and B1, the slope, is here, and SB1, the standard error for the slope, can be found here, 0.382497. The test statistic for the slope is B1 over SB1, and we can take B1 and SB1 right off of the Excel output, 4.74 divided by 0.3824, and we get 12.39905. We can also look at the t-stat column, labeled test statistic, t-stat column, and we can see 12.39905 right there. So we don't even have to do the calculations. It is given to us right on the Excel output. Finally, we don't have to look up the p-value either. It is given to us right over here. under the column labeled p-value. We can see it is 1.67e minus 0.06, and that means that the number is very close to 0. You would move the decimal place to the left 6 spaces. Minus 0.06 means left 6 spaces. And that gives us a very, very small number, very close to 0, indicating support for the alternative hypothesis, that the slope is not equal to 0. If the slope is not equal to 0, then there is a significant relationship between x and y, hours studied and grade on exam. The last thing we can look at on this output is the confidence interval estimate for the slope. At 99% confidence, we calculated a lower 99% interval of 3.4592 and an upper value of 6.026. And there it is. That concludes our tutorial for part 2, simple linear regression. Thank you, and I hope you enjoyed this video.